So I am Seth Redmore. I am Chief Marketing Officer of Lexalytics, and this is what I'm going to talk about. So who is Lexalytics, and why exactly are we here talking today? How's our stack work in terms of NLP? How we can fit machine learning and text analytics together and think about them both as separate problems and problems together. And I think there's a couple really important points there that I want to get across. Text and why it's really annoying to work with in a machine learning context and some of the frustrations we had with it. The clustering and extraction process, some interesting results, of course. What else could we have done? And then talking about this sort of human-computer partnership. And that seems a little fuzzy right now, but as I get to that, it will become a little bit more clear what I mean. High-level Lexalytics. We were founded in 2003. We build a text analytics engine. We are used primarily for social listening. We power most of the top social listening, social marketing platforms. We power a lot of survey monitoring platforms. We build an engine. We are entirely focused on text. That's what we do. Billions of documents a day flow through our software at all of our customers, hundreds of millions through our SaaS service. We have a hybrid approach to text analytics. We use machine learning inside of our system. We use NLP algorithms, and we use pattern files, dictionaries. We basically pick the right tool for the right job to do the text analytics. We maintain about 40 different machine learning models that we distribute and update and stuff to our customers. So we are very, very heavily invested in machine learning. Before I get into this slide, I wanted to actually, I'll talk about this real quick. So the way our software is organized is sort of in layers. There's this base knowledge layer, and so the concept matrix and syntax matrix, these are unsupervised models that we've built. So the syntax matrix is actually a way for us to do very quick syntax parsing, kind of like dependency parsing of a sentence, based on matrix factorization of around 40 billion words of text. The concept matrix gives us semantics. So in order to interpret a piece of text, you need syntax, semantics, and context. And so those pieces are there. Then we pull the text apart. We tokenize it, break sentences, part of speech tag. There's a lot of layers to how we do the natural language processing. This all fits together into one thing that then produces results that can be used by other machine learning models. And this is one of the most important parts or points that I want to make in this presentation is that it's not NLP or text analytics or text mining, not NLP or machine learning. You'll find that I'm going to switch between NLP, text mining, and text analytics because the market's very confused about what we call them, and it's very irritating. So there's two real obvious ways that you can treat text with higher level machine learning. One is learn and then do the NLP for discovery. So do your machine learning first, use certain algorithms, and that's what we're going to be exploring today. And then the other side is NLP first, then learn for predictions. So one of my strong recommendations, whether you use our software or not, is treat the text or your unstructured data as a separate problem from the rest of your system. So because if you try and mush everything together into a single model, it's not going to perform as well as it would as if you treated the text or your video or whatever as a separate unstructured thing, got the structured data out of it, and then used that with your machine learning technology. So the reason why we decided to give this first one a try is when an analyst gets a big bucket of tweets dumped on their desk, that's the first question they need to ask is, okay, what's in here? Once you have measured some degree of what's important inside here, what groups naturally inside of here, then you can take that, build classifiers with it, and integrate those into predictive models. There's a lot of things you can do with it, but there's very often with unstructured data, particularly text, a phase where you have to explore it and understand it before you can really do a lot with it. And that's what I'm going to be talking about is how we've combined H2O and natural language processing to do this together. And again, the stuff I'm talking about with NLP, I'm using my software because, hey, I had it. But these things apply to any of the open source toolkits that you use. There are pluses and minuses to each of them. I mean, of course, I'd prefer you buy my stuff, but you can think about the stuff I'm talking about in very generic terms. So text and why it's irritating. So text has sort of medium dimensionality as opposed to video, which can have gazillions of dimensions to it. It's much like the Netflix rating data, where it is relatively high dimension, kind of medium dimensionality, but it's very sparse. So what I mean by that is of the 100,000 or 200,000 potential lemmas or word forms that you might have inside of a piece of text, how many are you going to actually hit inside of your corpus? Right? Even if this is a corpus of highly related content, you're still only going to hit a certain number of these, and it's going to end up being a fairly sparse matrix. Now, of course, the stuff from Wikipedia, okay, stop words, things like the, of, and, to, that, have, that's going to occupy a fair amount of that space. And so one of the things that you have to think about is reducing dimensionality, and I will talk about that in a little bit. So really, our game plan here, here's the game plan. Cluster and then extract, so that we can use the machine learning and use the machine learning capabilities of automatically grouping things in ways that humans may not consider. That's the really important thing here, is that by using machine learning algorithms, unsupervised algorithms, to put things into buckets, they may put them in buckets that I never would have considered. And that's really important for an analyst, because if you're only going on the stuff that you know and you know where it goes, then you're going to miss something. So post-clustering, what we wanted to do is extract terms, bigrams, and trigrams, so easy stuff. Themes are something that is relatively specific to us. I'll talk a little bit about that, but it's something that you could probably implement as well. Entities, so entities are people, places, companies, named proper nouns, generally speaking. And then the sentiment or tonality for that. So the idea here being that these clusters have been grouped, so what's in them? And give it to me in a way that I can do it without having to read everything that's in the cluster. This is a relatively important problem for a lot of people in sort of the PR space. This is an important problem for people who are dealing with social media, who are dealing with support calls. Group them, see what the commonalities are, do something about it. So here's an example of what themes are. So this is a piece of text that I just grabbed off the net about shutdown in government and Pope Francis addressing the government. And so themes you can think of as being hyper summaries. So they are, technically speaking, contextually important noun phrases. And so one thing I'm not showing here is each theme carries a score. So how important is this theme in this document? The longer the document, the more important the score becomes. For a tweet, you're not going to get a lot of themes, right? But it's the algorithm sort of fails nicely with respect to, okay, inside of a tweet, I'm just going to look for the most important noun phrase in the theme in the tweet. So these are the top themes that we extracted from here, and it just gives you sort of a big picture idea of what was this about. We call it the buzz. One of the fundamental problems with themes as we have implemented them is that they are purely based on the words in the piece of text that's being analyzed. Pluses and minuses to that. The plus is you can see the exact language that people are using. The minus is that if I were to get a theme like oil drilling and petroleum exploration in two different documents without some other higher level contextual knowledge, which we can provide through other means, or through something else, I wouldn't know to group those together into a single bucket. And so remember that point. The way these actually work, we take text, we go through this huge text preparation step. So we tokenize it, part of speech tag it, chunk it, meaning what are the phrases. We associate the phrases with each other, we associate the sentences with each other, and then we do a certain amount of contextual analysis. Candidate themes have patterns to them, so they're part of speech patterns. And so I'm giving you this detail so that if this is something that's interesting to you, you can get off-the-shelf pause taggers, right? And you can build something that will give you this sort of extraction using open source software. You tune them using the part-of-speech patterns, and then we score them using a particular algorithm based on something called lexical chaining. Lexical chains are noun relationships inside of text. So synonyms have the highest score. So if you see chocolate and chocolate, that's the highest possible score. If you see chocolate and candy, slightly lower score. So if it's an antonym, it's going to be an even lower score. But it allows you to trace the thread of a particular thought, if you will, or chain of thought through a document and associate things inside the document. And so this allows us to score themes for longer documents. So that's the themes. This is what we're, one of the important things, and I'm harping on this now because we're going to be focusing on themes a little bit later on. So H2O, along with most everybody else, supports K-means clustering. So K-means, sure, you're all experts in this sort of stuff, but it's basically find a certain number of center points, and you have to decide how many clusters you want. That's an important point. But so that the distance between the members of the cluster are minimized. Basically, find your circles where this stuff fits inside of the circle and the distance is small. It can be solved in a reasonable amount of time with fixed dimensionality and number of clusters. So we know the dimensionality of our system, and we know the number of clusters because we tell it. So there are really three steps here. One, decide what we're going to cluster on. That's an important step. Initialize the set. So H2O uses Kmeans++. So that's a particular way of setting up the set so as to help you converge faster. And then run an optimized algorithm on it. We ran this straight in an H2O cluster. There are 2 test data sets that we ran, and these, I want to note, are relatively small data sets. We could run these on hundreds of thousands or millions of tweets. This just happened to be, something that I happen to have. They were data sets that we had reasonable understanding of. And so that was important for my perspective to see, okay, is this completely loopy what we're getting out of here? Or is this something that can actually provide value? Because this is all proof of concept. This is just, okay, is this something that holds together? Is this something that works well for us? And so what we want to know is, are there any natural, interesting groupings of the content that we should be aware of as an analyst without having to go in and make those groupings ourselves? And that's a really, really, really important point. So, dimensionality versus sparseness. Because of the nature of the text and its irritations, the sparseness messes things up. So we tried several different ways to just directly cluster. And so it's just like, great, let's try it. So we tried it on terms, we tried it on stemmed and unstemmed terms, bigrams, stemmed and unstemmed, themes, stemmed and unstemmed. So if you don't know what stemming is, it's just basically pulling the ending off of, cat and cats. So cat would be a stemmed term. Every one of these got a single mega cluster. So that's not good. So that means that the data is too high dimensional and sparse. There was no way for the K-means algorithm to really grab onto anything in order to try and find the similarities necessary to put things into the clusters. So that was failure number 1, 2, 3, and 4. Principal component analysis is one of the tools native to H2O. So we wanted to try and keep as much of sort of the clustering and such inside of H2O as we could. So PCA reduces dimensionality, so it finds this first principal component. So the first principal component is what accounts for the most variability in the data. And then what it does is it finds the next axis that accounts for the most variability. It has to be orthogonal. It goes through n of these until you tell it to stop, basically, or it converges. We ran this for over a week, and we were given a pretty hefty cluster to run it on, and the cluster ended up crashing after a certain period of time. So this is not, therefore, appropriate for this problem. Now, I'm sure there's people in the audience going, well, there's sparse PCA, and there's other ways to do reduced dimensionality. Yes, there are. But we just wanted to get over this particular hump. And so what we decided to say is, let's try something that's getting a lot of buzz and press right now. So Word2Vec. So Word2Vec, it's an open source tool set for really understanding probabilities of words occurring together. And so as you calculate the distance in between the words, based on a whole training corpus, it allows you to say, okay, these things are probably going to belong together. We used, you have to set up a certain number of dimensions. We use 300 dimensions, really because that was on the Google model that we downloaded and used. You can train this to be however high dimensionality you want it to be. And we're actually looking at potentially doing that in the future. So, great. We ran word-to-vec. Now we're not getting one big cluster anymore. We have to figure out how many clusters are optional, or optimal, not optional. We're just doing discovery here. We didn't want to spend a lot of time running all kinds of experiments and say, okay, let's try all these different cluster spaces. So we did 8, 30, and 100 because we like those numbers. And what I'm going to show you on the next few slides is the sort of results that we saw from this, some of the interesting extractions that we got. So this first slide is politics 30. It's from one of the 30 clusters, politics one. So these are the terms, the bigrams, and the trigrams that are most popular inside of there. Now, there are things you could do here to clean this up and say, okay, I don't want to consider trigrams that are hashtags or at symbols, right? That's very easy to do. But let me show you what's on this next slide. So, and pardon the language on the slides, we're dealing with Twitter. These are really related things, mostly speaking. It's like there's kind of two concepts bucketed together here. So there's the immigration, and then there's the Trans-Pacific Trade Partnership. And so these are kind of multi-country things, and that's why they sort of become inside of this one cluster. So these are related concepts inside of this cluster that we just generated automatically and we extracted. Now, when we look at something that's similar, but from the one where we did 100 clusters, most all of them are related to immigration. There's one, big money donors, and it'd be interesting to understand exactly why that one happens to look like that and why that one was here. But this tells me as an analyst, these are things that maybe I want to put into a category or build a classifier around immigration issues, right? These are the terms that are going to be most popular and most used having to do with immigration issues. And I may not have been able to think of all these myself. So here's another cluster, so with the trigrams and bigrams, but then let's get to the themes and such. So this is, clearly about Bernie Sanders. Win his great start, inviting folks, great day, convention crowd, cheers, clear winner. So this is all about how he started out. And so here's this related cluster about what's happening with Bernie Sanders. So there were some pathological clusters. There were clusters that had like one thing in them. And there were other clusters that didn't have quite as clear of a message to them. But with some tuning and tweaking, I'm fairly sure that we could get something where the clusters were all related. I do want to show one example of the Samsung stuff that we did. So there were two here. So on the right, I looked at sentiment. I looked for the two highest sentiment things. Now, the left one is broken. And it's very interesting how it's broken, in that most of the stuff in it had to do with the fact that they had supply rollout problems. But the Android smartphone profits outweighed the sentiment in the rest of it. And so this is one of the things that we have to sort of work on and look out for. I can see how they are related, profit being related to supply. But this is the kind of thing where it's like, okay, I'd probably try more clusters. And on the right, this high sentiment having to do with this luxury aspect of it. The limited edition, the leather sleeve, waxed leather, soft skin. It puts the lotion on the phone. So these are all things that, again, people are talking about as being really important to them that they're really positive about. So this is interesting because if you're trying to figure out how you did with your launch in the Samsung, it's cool. So what else could we have done? Different cluster sizes, semantic meaning of the themes for associations. We do have some semantic technology. There's other ways that we could do that. Pre-sorting on queries of or candidates or topical queries. And I'm going to talk about what that means in a second here. This is what I mean by human-computer partnership. And this is an interesting process that we're going to spend more time working on, which is you take your text, You reduce the dimensions, you cluster it, loop that process if it's broken until you get reasonable clusters. Extract, examine. When you examine the text in it, pick a lens and say, okay, I want to look at this content through the lens of this particular entity, say Hillary Clinton. What do the clusters contain that are about her? Or I want to build a classifier about immigration and say, what are people saying, specifically about immigration? Are there people that are more involved in that conversation than others? Are there other topics that we should be discussing? So this is a very sort of iterative process that you can use that goes from using the unsupervised clustering through extraction and loops it back through. So in summary, text analytics, we rely very heavily on machine learning to do its job. It can come before or after other machine learning processes. And so it is something that is additive. We believe that you should consider text or other unstructured data as a separate problem, deal with it, reduce it, extract it, and then manipulate it inside of the rest of your systems. Reducing the dimensionality of the text is important. Principal component analysis wasn't suitable, so we used word2vec, like I said before, sparse PCA might work. And then for discovery, you can loop, take a lens, and then come back through and do your clusters again. So last but not least, thank you very much to H2O. They were really fantastic during this process. They were really responsive, really professional, helped us through a couple hitches that we have. Could not have been happier with the support we got. I wanted to thank the head engineer that did the work on this. Thank you guys all for listening. Happy simultaneous Diwali and Veterans Day. And please, if you want to, hit me up on Twitter at @sredmore or send me an email at lexalytics.com. That's all I got. Thank you.
All right, we've got time for a few questions. So we have questions.
I just have a question about NLP analytics of languages like Japanese and Chinese. Are you able to handle those, or you only use languages outside, process languages outside of this?
Oh, no, we totally. So I used English as an example, but we've got, like, depending on how you count it, if you're a marketing guy like me, you count it as 22. If you're an engineer, you probably count it as like 19. So depending on whether you consider the different forms of Indonesian to be different languages or not. But no, so like Chinese, we support traditional simplified, so it's a lot of different languages. That was your question, right?
Yes, I use the same methods, or you use different methods for those languages?
Sorry?
I use the same methods, like stemming and
yeah.
For Japanese and Chinese. That
we have
totally
yes, and that's
different.
actually an excellent question. So for 3/4 of our languages, yes, we do. For 1/4 of our languages, we use pure machine learning and the ability to do queries. So we've got tier 1 and tier 2 languages. So for example, Swedish, we did as we call a tier 2 language, where we built up a sentiment model, a sentiment classifier, plus we built something where you could do query-based categorization. But for most of the rest of our languages, we have the whole thing in part-of-speech tagging, tokenization, all that sort of stuff for it. Like for Chinese, we had to build a machine learning-based tokenizer for it because there's no white space.
Hello?
Other questions?
Yeah. So the word2vec that you used is context dependent, right? So from Google, they must have trained that model on some other context of.
Yeah, it was like it was news, primarily news.
Yeah. So you used it on something else. I was wondering that how that could have hurted your clustering or whatever.
Oh, sure. And it was absolutely. So one of the things we've been bouncing around is we got a bunch of tweets. Why don't we train up our own word2vec for it? It was a matter of basically time and convenience. So Twitter has, as we may have noticed, slightly different language than well-written news articles. And so, yes, I think that it definitely affected things, but not to the point where it was completely busted. We just wanted to see if the word2vec process, way of doing things, was even a reasonable way of approaching it. But yeah, absolutely. It's something that we are very much looking into is, do we want to train it ourselves?
Thanks.
And actually, a word on that. So with word2vec, I have a lot of people approach me about word2vec. Oh, should I be using this and stuff? For a lot of folks, they don't actually have these massive corpora to train on. And if you don't have that and you train Word2Vec, you're basically training it weakly in a weak sense. And so you might very well be better off to just take a pre-existing trained system, so something that was trained on Wikipedia or a news source, and go with that, because a lot of what it has embedded in it is the word meanings. And yes, there are slight subtle differences to how things are used in, let's say, tweets, but if you just have a small number, then you're not going to get very strong training, and you know, you might as well come up with a well-trained, slight differences in meanings than poorly trained system, you know, because you just didn't have enough to feed it.
Yeah, I completely agree with this. The one thing I would add to it is the reason why we'd be looking at it is we're in the business, and things like emoji and acronyms and stuff weren't as prevalent inside of, you know, the Word2Vec model we were using, but it did really well for what we were using. It did well enough for us to get some interesting clusters out of it.
Hi, how do you take in some sarcastic sentences? Like, how would you analyze them?
How do we analyze?
Like sarcastic sentences or like sarcastic comments?
Yeah, we do it really, really well. So poorly. Sarcasm actually, and this is something that I think would actually be a really good topic, and I brought it up for the panel, for the NLP panel later. Sarcasm, in order to get sarcasm or humor, you have to understand, you have to have context. I think you could probably philosophically prove that sarcasm does not exist without context, right? So if you purely see something that says, I love the Apple Store, all you can say is, dude loves the Apple Store. But if you see before that, you know, I waited in line for 3 hours and the genius was an idiot, then you know that is. So you have to have context. And so I believe the only way that we're going to get to the point where we can really handle sarcasm and humor is by taking steps towards understanding the context of individuals. First, starting with cohorts of people that, you know, okay, this group of people are probably going to be saying these sorts of things, but then drive it down to the individual and say, okay, this person is generally positive about this and then really negative, or are they being sarcastic? So it has to have context, and so it's definitely an ongoing way of doing it.
You were talking about tweets and analyzing those microblog data.
Yes.
I'm wondering what recommendations you have for pre-processing those data before bringing them into machine learning, dealing with emoticons, slang, issues like that.
So there's two answers to that question. One answer is a lot of that stuff we handle ourselves internally, and so we understand emoji carries certain sentiment. We understand we're able to expand acronyms. But having said that, there's a couple interesting things that you can do in terms of replace if you know the emoji because it's Unicode, right, and it's relatively consistent, and so you could replace that with a sentiment phrase. You could also expand the acronyms if you have an acronym list, which would help, and you can get those from a lot of different places. Same with emoticons, so you could replace that with some sort of sentiment-bearing phrase, right? So that you take it all down to words. That would be one thing I would do. Another thing that we do internally is we expand hashtags. So hashtags are used in two ways. One is like we're using them today to mark an event, and the other is instead of an exclamation point, so like hashtag I love Lexalytics. So we tear those apart, and so that's actually a much harder problem than the other things that I mentioned, but that's one of the things that we do. But in terms of replacing some of those things you see in there with known phrases or phrases that that will carry a particular weight is a useful thing to do.
Great. So could we all thank our speakers?
Yay! Thank you.